There we go. Okay, so thank you again for coming to our regional seminar, analysis and PDE seminar. I think that Daniel did all the great thanks and welcome and everything in the morning, so I won't repeat it. Instead, I'll just say welcome to the afternoon session. Thank you again for attending. And I'll introduce the next speaker, which is, I'm very sorry if I butcher your name.
It's okay.
Chunxi Jiao, I don't know.
Yes, it's good enough.
Who will be speaking about the solution of a stochastic Landau-Lifshitz-Slonczewski. Oh my God, another name that I can't pronounce. Slonczewski equation. All right, please take it away.
Yeah, thank you. Thank you for the introduction. So this talk is based on joint work with Ben Gollis and Glen from Monash, Ben's from UCIT. So just a quick introduction on Landau-Lifshitz equations. Landau-Lifshitz equations describe the dynamics of magnetization. The situation is this. In a ferromagnet, the magnetization vectors M tend to align spontaneously, giving a non-zero net magnetic field, sometimes called the saturated magnetization. So these vectors, when modeling, can be scaled to magnitude 1 under this saturation constraint. Then when the ferromagnet is placed under a reasonable temperature, the main component for its free energy will be the exchange energy in the form of some gradient squared times a constant in the integral. The cross-bounding effective field will just be the Laplacian times a constant. The effective field basically means that if the vector M is parallel to H, then the energy is minimized. For the ease of interpretation, we can view a single M vector just as the spin of a single electron. In 1935, Landau and Lifshitz proposed the following equation for M. There is a precession term, negative M cross the field H, or simply the Laplacian, which represents the torque exerted by the field on the electron. There is also a small damping term. Alpha is usually a positive small constant, which counteracts the precession to explain the phenomenon that the magnetic field magnetization vector gets aligned with the effective field over time. This is closely related to other classic equations. If we take alpha to be 0, then it reduces to Heisenberg's equation. And it's well known this is equivalent to the nonlinear Schrödinger equation when the problem is one-dimensional. On the other hand, if the Laplacian is well defined, and if the magnetization vector M stays on the unit sphere, then we can rewrite the damping term, which is this double cross product here, as the sum of Laplacian and gradient squared times M itself. This is the heat flow of harmonic map into the unit sphere. In 1996, Slonczewski modeled, here we go, Slonczewski described the additional spin transfer torque term that's induced by an external electric current injected into the ferromagnet, adding this transport term negative V times gradient into the equation. So V is a function of time and X that describes the density and velocity of the electric current. If M has constant magnitude, as the model assumes, we can also rewrite this transport term back into the double cross product form, which is convenient for the proof later on. The situation that's described by Slonczewski's modification here is that when a collection of electrons, so a current, with electron spins previously aligned, flow through a ferromagnetic nanowire, which has data rarely stored in it as some magnetic pattern, so the red and blue blocks. This incoming surge of electrons will exert torque on this pattern. So like the domino effect, the pattern essentially gets moved down the wire and it gets recorded as bits 0 or 1. This is how the racetrack memory works. I'm not sure if you can see the heading of the figure. In practice, these magnetic storage devices are very small, nanoscales, so they are subject to thermal fluctuations. This leads us to study a stochastic version of this LLS model with noise in the current for an infinite nanowire. What I mean is that instead of just v dt, we propose v dt plus g dw, where v is a function bounded by a constant capital C v. W is a real-valued Wiener process defined on a filtered probability space. The small function g is real-valued, bounded with bounded derivatives, and we also write the bound as capital C with a subscript g. To simplify the notation, let's call the right-hand side of the deterministic LLS equation to be capital F, and let capital G denote the diffusion part, which is equal to small g times this double cross product with the gradient. We choose the Stratonovich differential here just to keep M on the unit sphere for the formulation, because rules of ordinary calculus still holds for Stratonovich differential. If we calculate dm squared, then it's clearly equal to 2 times the dot product of M and the right-hand side of this equation, which is in the form of a cross product with M. Then by simple cross product property, this is equal to 0. In other words, if the initial point M0 starts from the unit sphere, then the magnetization process M stays on the sphere over time almost surely. We also assume that the initial point M0 has a square integrable gradient, so it's in this H1 dot space. Transforming this into the more familiar Ito form, we have an additional Stratonovich correction term denoted by capital G tilde here. Capital G tilde has some higher orders, like dm squared or M cross Laplacian. What we aim to show is that under a smallness condition for this constant capital CG, so capital CG is the bound for the function small g and its derivatives, we show that there exists a unique solution to the stochastic LLS equation. In the sense, there is a system consisting of a filtered probability space, a real-valued F-adapted Wiener process W, a progressively measurable process M, such that M takes values on the unit sphere almost surely. It satisfies the stochastic LLS equation with continuous paths taking values in a weighted L2 space, and has regularity described here for the L2 norm of its gradient and L2 norm of the Laplacian under time integral. Moreover, the solution is pathwise unique. The steps of the proof are outlined here. We are going to take a lattice approximation in a similar way to how the deterministic LLS equation is discretized in the paper by Murphy and Tushnik. Then for the discretized equation, we show it has a unique solution which satisfies certain uniform estimates in a similar form to part 3 regularity given above. Then to map back to the continuous model, we will take a suitable quadratic interpolation and find a converging subsequence of processes. What remains is to show that the limiting process solves our stochastic equation and is pathwise unique. Many of the convergence and the uniqueness arguments follow from arguments in these papers by Jechniak, Goldzis, and Jakaraj. So we just adapt some of the arguments. A small remark to make is that the smallness condition on CG, which will be made more explicit later on, is quite natural to guarantee the existence of solution. For instance, if we just consider the Laplacian bit in the drift, then the cross-bounding heat semigroup, the one highlighted here, will only make sense if the coefficient alpha minus half g squared, small g assumed to be a constant here, is positive. So g squared has to be small compared to alpha. Following the outline of the proof, the first step is to discretize the equation. So we fix a mesh size h. Then on a uniform grid, we define the forward-backward discrete gradient, d plus h, d minus h, the symmetric gradient, dh, discrete Laplacian, delta h. Then we consider the following equation on the uniform grid with the discrete symmetric gradient and the discrete Laplacian. So this FH, G tilde H, and GH just denote the discretized version of the original F, G tilde, and Gs. Now we define the space capital EH to be the intersection of the discrete L infinity and the discrete H1 dot space. We also define this curly E to be the space of capital E valued progressively measurable processes. This comes our first lemma. For every fixed H, we show that there exists a unique solution MH of the discretized equation in the space curly E that takes values on the unit sphere almost surely. The proof follows from standard arguments. We just give a quick overview here. So for every fixed H, we will approximate the corresponding discretized equation by Lifshitz modifications Fn, G tilde n, and Gn. Then for every n, we show that this approximate equation admits a unique solution Mn by checking that the operator capital An is a contraction. So to check that, we need to deal with this stochastic integral term. And the way to do that is to see that it's taking values in this H1 space, and then we can compare its H1 norm to the E norm to see that this term here satisfies a similar Lifshitz property, just like the Fn and G tilde n parts. As aforementioned, we can also check the Mn squared to see that the solution Mn stays on the sphere. Finally, let tau n be the time that Mn leaves the ball, first leaves the ball of radius n. Then by checking Mn is indistinguishable from Mn plus 1 up to the stopping time tau n, we can essentially paste Mn together with Mn plus 1. As tau n goes to infinity, we can take Mh to be the limit of the Mn's, which will be our unique solution for the discretized equation. Now that we have the discrete solution MH, we derive some uniform estimates for it. We would like to have uniform estimates for its gradient as well as the Laplacian. To this end, we apply Ito's lemma to the L2 norm of the discrete gradient D plus M. The equation is given here. The first and the third term comes from integration by parts. The second term, so this 1/2 part here, is the Ito correction term. What we aim for is Grunwald type inequality at the end. So we can first estimate the diffusion part by Coder-Davis-Gundy inequality, which is given here in its original form. This inequality gives an estimate for the L2 norm of a stochastic integral. So we can apply this inequality and expand this capital G to see that the diffusion part can be estimated by the L2 norm of the discrete gradient and the L2 norm of the cross product M cross Laplacian under the time integral. Then, given a uniformly bounded initial point M0 for small epsilon and small cg, satisfying these two inequalities, we show that the discrete gradient D plus M is bounded in this L2p omega LH2 space. And similarly, the Laplacian of MH is bounded in this LP omega L2 time LH2 space. The details of the calculation are very long and so omitted here. Now that we have a discrete solution MH, we have its uniform estimates, we still need a suitable interpolation to transform this into a continuous function. Let xk be equal to kh, which are the points on the discretized real line. Then for a discrete function u, we let u hat be its piecewise constant interpolation, u tilde be its linear interpolation, and u bar a suitable quadratic interpolation with a midpoint form for its zeroth order terms. By construction, this x minus xk, they are less than or equal to h, so we can see some cancelling happening later on. We observe that for the quadratic interpolation, it's actually twice differentiable. Its first derivative is continuous, It's indeed the linear interpolation of the discrete backward gradient. Second derivative is simply the discrete Laplacian. Let's quickly review how the arguments work for deterministic Landau-Lifshitz equation. We would start with weak convergence of the linear interpolation U tilde in this L2 time H1 space, and weak convergence of the time derivative of U tilde. They will give, by Orban's lemma, the strong convergence of U tilde in a L2 time, L2 local, or L2 weighted space. This strong convergence of U tilde in turn implies strong convergence of U hat, the piecewise constant interpolation. Then we can just do convergence from the equation of U hat, which is essentially the discretized equation, to the original Landau-Lifshitz equation. In a stochastic setting, we need to be a bit more careful. First of all, we don't really have a well-defined time derivative for the stochastic process MH. However, a similar compact embedding result still holds for fractional time derivative case. So we'll be focusing on this fractional Sobolev space, W beta P. Next, our uniform estimates, so those bounds we obtained on the previous page, they are on a L2 omega space. So we need to bridge between weak and strong convergence over the probability space. This can be done by Skorohov theorem, which will be stated formally later on. We also have a gradient term in the stochastic integral coming from the transport in Slonczewski's spin transfer talk. So we will choose the quadratic interpolation M bar instead of M tilde, the linear interpolation, to obtain strong instead of weak convergence for the gradient. The flow of arguments will still start from finding a suitable space, capital E0, that the quadratic interpolation M bar takes values in. We can easily verify that the same set of uniform estimates hold for M bar. That is the two inequalities here. Then by the interpolation inequality, which is the one here, we can obtain an estimate for the L4 norm of the gradient of M bar under the time integral. It's also worth noting that although this quadratic interpolation does not take value on the unit sphere, it is still bounded, and we can show that its vector length converges to 1 almost surely as h tends to 0. Taking these estimates, we can write down that the quadratic interpolation M bar lives in the H2 dot space as well as this L2W, which is the weighted L2 space, for almost all time t. The weight function rho W in the definition of weighted space is given here. It's conveniently smooth, positive, bounded by 1, it vanishes at infinity, and it decreases with W. Now let's turn to the weak time derivatives. Let's rewrite M bar in terms of I0, I1, and I2. I0 consists of approximations of the initial condition M0. I1 consists of the other drift terms, so the small f is defined to be the capital F plus half capital G tilde. I2 just collects all the diffusion part. Okay, now recall that x minus xk is less than or equal to h. As aforementioned, there will be some cancelling in the blue terms colored all over the place. This will leave us with only 0th order terms like m0, small fh, and capital GH in this I0, I1, I2 terms. Then by the previous uniform estimates, we see that the L2 norm of this small f under time integral is bounded under the expectation. This gives us a W12 time estimate for I1. Similarly, by an isometry result here, we see that I2 takes values in this fractional Sobolev space W beta P for P greater than or equal to 2, beta less than a half. But we also notice that I0, so all the approximation of M0s, is not in L2, but in L2W, the weighted space, because M0 is taking value on the unit sphere. So we relax all the L2s to L2W. Then by another continuous embedding from W12 into W beta P, we summarize that M bar is in this W beta P time L2W space. Now we have two estimates for the quadratic interpolation M bar. Combining these two estimates, we see M bar is essentially in this intersection of L2 time space and this W beta P space. Let P be equal to 4. Then for weight parameters W1 less than W2 and a suitable parameter beta, we can take the space E0 to be this intersection of the two spaces. Our next step is to find a space capital E that E0 is compactly embedded in. By results from Simon, Vanderlei, and Gottschalk, we find capital E to be the intersection of a L2 time H1W space and a continuous time XW to the negative half space. Here, the H1W is the weighted H1 space with the same weight function rho W. It's often denoted as XW to the half to account for the fact that it's the domain of the square root of the Laplacian. So its dual is denoted with the negative power at the top. From this compact embedding, we see that the laws of the quadratic interpolations on this Banach separable space capital E are tight, in the sense that the laws concentrate on a ball in E0 that is compact in the space E. Then by Prokhorov theorem, there is a subsequence of M bar H, which we keep the same notation, where the laws of this subsequence and the Wiener process converges weakly to some probability measure mu on the space E times the space of continuous functions in time. Another way of saying this is that the random sequence of this pair M bar HW converges in distribution. As aforementioned, we will need to bridge between weak and strong convergence of the probability space. And this is done by Skorohod's theorem stated here. It tells us that although a random sequence taking value in a separable metric space may only have weak convergence, converging in distribution, we can always find another probability space with another random new sequence that has the same laws as the original sequence, but now converging almost surely. Now we can take this at n to be our pair M bar HW, and this space capital S to be the product capital E times C. I'll just apply this Skorohod theorem to see that there exists another sequence, MH star, WH star, defined on another probability space, such that they have the same law as the original quadratic interpolation and Wiener process, and they converge almost surely with the limit M star and W star. Thanks to the definition of capital E here, this HW, H1W, I'm trying to highlight, there we go. We now have the convergence of the gradient directly. So we have a new process MH star as before we collect its properties. First, we recall that the quadratic interpolation takes values in the space B almost surely. Then by Kratowski's theorem, Browse sets of B map into Browse sets of E, or you can view it as continuous embedding. Since the laws of M bar and MH star are equal, we can also assume that MH star, the new process, takes values in the space B almost surely as well. As a result, uniform estimates of MH star just follow from those of M bar. Namely, we have estimate for MH star in the L2 weighted norm, for its gradient in the L2 norm, also its gradient in the L4 norm on the time integral, L2 norm of its Laplacian on the time integral. From the second and third estimate, it's easy to see that there is a weak limit capital X of the MH star and a weak limit Y of delta MH star in these L2 spaces. It's worth noting we don't actually have L infinity norm for MH star itself. We have instead L infinity estimate for the product of MH star and a weight function. This will be sufficient for the convergences later on. Now, on the previous slide, by Skorokhod theorem, we obtained pointwise convergence on the probability space. And now we have uniform integrability conditions here. Combining them, we have a strong convergence from the approximating process MH star to the limit M star in this L2 omega star, L2 time, L2 weighted space. And similarly, we have the strong convergence for the gradients immediately. By the uniqueness of weak limit, we actually have a dm star equals to capital X, taking values in this L2 space. Then by the definition of weak derivatives, we obtain weak convergence for the Laplacian in the same L2 space. We can actually improve the estimate for the gradient of the limit by Fatou's lemma, which is this inequality here, and by the estimates in L2W intersecting H1 dot for the approximating process MH star. This is saying that the gradient of the limiting process satisfies essentially the same estimate as the approximating process. It has a finite expectation for the gradient in L2 norm to the pth power. Suppose that our M star is a solution of the stochastic equation, then we would have the two regularity statements in the main result already. Moreover, we see that for this limit process, weighted L2 analog for the convergence of vector length also holds true under the strong convergence that is highlighted there. So M star takes values on the unit sphere almost surely. Now we need to see that M star is in fact a solution. What we need will be convergence from the equation of MH star to the stochastic equation. Since MH star and M bar, they have the same laws, so we can just look at the equation of M bar for the approximated drift and diffusion terms. So this is the equation here. The slight modification occurs in the drift terms and the diffusion terms by replacing the original real valued functions b, g, g prime by the piecewise constant interpolations. There are also some remainder terms that come from the difference between the two types of interpolations m hat, the piecewise constant one, and m bar, the quadratic one. But they don't really matter because they converge to zero either weakly or strongly in suitable L2 spaces.
Just about 2 minutes left.
Okay, I'll wrap up. Yeah, so now we can prove a weak convergence from the new drift term to the original drift term, and strong convergence from the new diffusion term to the original diffusion term. The proof just relies on the convergences of the components that we showed earlier on. Now, with this lemma, we can show that M star indeed solves the equation. We can define the right-hand side by this capital M star, and we can write down a similar expression for the approximating process MH star following the equation satisfied by the quadratic interpolation. So there's some remainder terms. All we have to show is that W star, the limit, is a well-defined Wiener process, and we have a weak convergence from this approximating process both to the right-hand side and to the left-hand side. So the convergences again follow from the estimates we had earlier on. So I'll skip this. Once we have this equality proving that M star is indeed the solution, we can turn to the uniqueness. For uniqueness, we just have to see that the difference between two solutions is equal to 0. So this follows from estimates, again from previous slides, and an important exponential transformation from idea in this paper. So with this transformation, the power here will cancel with the estimate of drift, which is highlighted there, leaving us with only a martingale term on the right-hand side. So the expectation of martingale is 0, telling us that the transformation is 0, telling us that f squared is 0, giving us pathwise uniqueness at the very end. So this is the end of the proof and end of the talk. I hope I didn't go over time. Here are some references, and thank you very much for your attention.
Thank you, Chunxi. I'll do my clapping react. That was a brilliant talk. I'm sorry for interrupting. I never know what to do with that. If I should say
That's
anything
okay.
or not. I saw there was like slide 12 of 18, and I thought, oh, I don't know if I should say anything.
Sorry for rushing at the end.
No, it's totally fine. It's a very nice talk. We have time for questions. So if anyone has a question, please feel free to unmute. No, I've got a question. So as far as I understand it, you have a stability result with a small amount of noise. What happens when there is a large amount of noise? Is this false, or is there some sort of critical threshold?
I don't think there will be existence when G is too big.
Do you know exactly how big, or are you there's?
So that's probably related to how sharp the bounds I provide are. These bounds here are not really sharp. It depends on the choice of discretization in the proof. But if CG violates these two inequalities, then at least from the proof of this lemma, there will not be existence of solution at all.
Cool.
So the main point is that CG has to be, the highlighting is not really working, but yeah, the main point is that CG squared has to be comparable to this damping constant alpha.
All right.
If that answers.
I have one question.
Yeah, go ahead, Daniel. That does answer my question. Thank you.
So what is omega actually here? It is, and what are the boundary conditions of this?
Oh, it's on the real line. There's no boundary condition.
Yeah, okay.
Sorry if I didn't write it.
No, that was exactly what I wanted
yeah,
to.
there we go. Yeah.
Yeah, on
It's
the real
entirely
line,
the real
full
line. Yeah.
real line.
Full
Okay.
real line.
Yeah.
Yeah, and the omega is small omega is the event in the sample space, and
No, this is clear, but I mean, I wanted to know you are in one dimension basically.
Yeah, it's in one dimension.
Yeah.
The entire real line.
Awesome.
Very interesting.
Are there any more questions? Okay, if not, we'll have like a, I don't know, a 2-minute break before the next
I'll
one.
stop sharing.
Yeah, thank you, Chunxi. We can go to the toilet or something. I don't know, pour yourself a drink. All right, I'll thank you again.
Thank you.
All right, we'll resume in 2 minutes.